Hello everyone, welcome back to the course Vector Calculus and Complex Analysis. Myself Dr. N.CH.Ramgopal, working as Associate Professor in Mathematics in the Department of Humanities and Sciences, MLR Institute of Technology, Hyderabad. Today, I am going to introduce a method to evaluate a line integral of this form, integral minus infinity to plus infinity f of x dx. So, here in the last session also we have discussed about evaluation of real definite integrals by contour integration, and there are different forms. In the last session we have discussed to evaluate a line integral of the form integral 0 to 2 pi, a function having sin theta or cos theta or both. So, here this function of theta is reduced to a function of z using this transformation, and then by finding the poles and residues and using the residue theorem, we have evaluated the given line integral. Similarly, today I am going to introduce the method of evaluating the line integral, which is of the form integral minus infinity to plus infinity f of x dx. So, either the limits are from minus infinity to plus infinity, or else we can consider 0 to infinity also. So, the minus infinity to plus infinity, if the function is even, we can reduce it to 2 times of 0 to infinity if the function is even. So, integrals of the form minus infinity to plus infinity f of x dx or 0 to infinity f of x dx can be evaluated using the residue theorem. So, here coming to the method of evaluation. To evaluate the line integral f of x dx from minus infinity to plus infinity, let us consider an integral f of z dz along a curve C, where this curve C is the closed contour consisting of a semicircle. So, here we can draw that x-axis, y-axis, 0 and the semicircle along with the real axis minus r to plus r. This is minus r, this is plus r. So, if you consider a point here, so this is the radius capital R, and we introduce a circle CR. So, here that CR is introduced, mod z equal to R. So, if there are no poles of the function f of z on real axis, then the circle mod z equal to R, which is arbitrary, can be considered such as there is no singularity on its circumference CR. So, this is the circumference CR of the circle mod z equal to R, but possibly some poles inside the curve. So, here on the curve, that means on the circumference, there are no poles, but there can be some poles inside the curve. So, if there are no singularities on real axis, then by residue theorem, this line integral C f of z dz is equal to integral CR f of z dz plus integral minus infinity to plus infinity f of x dx. So, the integral can be divided into two parts. One is on the circumference and within the circle. So, using the theorem, residue theorem, integral C f of z dz is 2 pi I into sum of the poles at its internal poles. Internal poles means the poles which are inside the curve C. So, here the integral along CR vanishes as r tends to infinity. So, as r tends to infinity, the line integral along CR f of z dz that tends to 0. As r tends to infinity, the line integral vanishes. So, the line integral along C f of z dz is simply 2 pi I into sum of the poles of the function f of z within the curve C. So, this is the process of evaluating the line integral of the given function. So here we need to split the integral into two parts. One is along CR and one is from the limits from minus R to plus R. Here along the axis and on the circle circumference. So let us discuss the same method through an example. So here evaluate integral minus infinity to plus infinity dx x square plus a square whole square. So coming to the solution part, to find this, let us consider the integral C f of z dz. So that means integral C f of z dz is integral C 1 by z square plus a square whole square dz. So in terms of z we have considered, and let C be the curve, be the contour consisting of semicircle CR. So then the line integral f of z dz is equal to along CR f of z dz plus along minus R2 plus R, so which is the real axis f of z dz. So that implies, now as R tends to infinity, the line integrals along CR that vanishes. That means that tends to 0. So therefore, so here we can consider the given as integral minus R2 plus R f of z dz. So the given integral can be calculated by finding this. So here what is the function f of z? 1 by z square plus a square whole square. Now to use the residue theorem, first we need to find the poles. So what are the poles? How to obtain the poles? By equating the denominator to 0. Z square plus a square whole square is 0. So z square plus a square is 0. Z square is minus a square and z is plus or minus ai. And here it is very clear that z equal to ai only lies inside the curve, since we have considered the upper part of the semicircle. So that's why only plus ai lies inside the curve. So here this is minus R to R real axis and this is a semicircle, and here CR is mod z equal to R. So since we are considering only the upper part, this z equal to ai lies inside the curve, z equal to minus ai lies outside the curve. So it is enough to calculate the residue at this pole. Now residue of f at z equal to ai, and also here z equal to ai is a pole of order 2. It's a pole of order 2 since here we have whole square. Now what is the formula to find the residue of a function f of z at a pole z equal to a which is of order m? The formula is 1 by m minus 1 factorial limit z tends to a z minus a power m into f of z d by dz of, so d power m minus 1 by dz power m minus 1. We need to differentiate m minus 1 times. So this is, put m equal to 2 here, 1 by 1 factorial is 1. So residue of f of z at z equal to ai is equal to, put m equal to 2 which is 1 here, and limit z tends to ai m equal to 2. So, the first derivative of, now what is the function actually here? F of z is 1 by z square plus a square, z square plus a square whole square. So, which can be written as 1 by z square minus ai whole square whole square. So, which is in the form of a square minus b square. So, a plus b, we can write it as a plus b into a minus b. So, z plus ai into z minus ai whole square. So, d by dz of z minus ai whole square into 1 by z minus ai whole square into z plus ai whole square. So, we need to differentiate this function. Here these two gets cancelled and limit as z tends to ai, the derivative of this, the denominator z plus ai minus 2 into z plus ai. So, this is limit z tends to ai minus 2 by z plus ai whole cube. Now, by applying the limit as z tends to ai, we get the residue of f at z equal to ai is equal to minus 2 by z tends to ai. So, 2ai whole cube minus 2 by 2ai whole cube, which is minus 2 by 8 a cube into I cube 4 times. So, minus 1 by 4 a cube into I cube can be written as I square into I, and I square is minus 1. So, minus 4 a cube I, and again these two cancel, 1 by 4 a cube I. So, this is the residue of the function, and by residue theorem, the line integral from or C f of z dz is equal to 2 pi I into sum of the residues. But here we have only one residue. So, from minus infinity to plus infinity, dx by x square plus a square whole square is equal to 2 pi I into 1 by 4 a cube I. These two gets cancelled. So, pi by 2 a cube is the final integral value of the given function. Now, coming to the next problem, evaluate the line integral minus infinity to plus infinity dx by 1 plus x square whole square. So, you can continue the same process similar to the previous problem, or else you can compare it with the previous one, dx by x square plus a square whole square. What is the answer here? Pi by 2a cube. Pi by 2a cube. Now, we need to evaluate minus infinity to plus infinity dx by x square plus 1 square whole square. So, that means a equal to 1 here. So, the answer is pi by 2 into 1 cube, which is pi by 2. It is a shortcut one using the previous one as a standard formula. Otherwise, you need to follow the same procedure. So, first we consider integral C f of z dz, which is along the semicircle and from minus r to r. As r tends to infinity, this first integral tends to 0. So, only this remains, and here we find the poles of this function f of z and identify the poles which are within C, then find the residue and use the residue theorem to evaluate the line integral. So, this is for today's session, and we will meet in the next session. Thank you.